Hello everyone, I'm Changfeng Ma from Nanjing University. I'm honored to present my work, Symmetric Shape-Preserving Autoencoder for Unsupervised real-sense point cloud compilation. Real-sense point cloud compilation presents a challenge due to the disparity between artificial datasets and real-sense datasets. Additionally, obtaining ground truths for real-sense partial point clouds is often unfeasible. Moreover, existing unsupervised methods struggle to preserve the intricate structure details as shown in the figure. We introduce USSPA, a novel network for real-sense point cloud compilation. Our approach leverages a symmetric learning model, a refinement autoencoder, and a point feature discriminator to achieve superior results that are both uniform and accurate, while preserving the symmetric shape of the input data. We also propose an evaluation method specifically designed for assessing the quality of unsupervised real-sense point cloud compilation. Point clouds are gaining popularity as the standard output of 3D scanners. Complete point clouds play a crucial role in various downstream applications, including part segmentation and reconstruction. However, obtaining complete point clouds in real-life setting is a formidable task. In practice, we commonly encounter partial point clouds. Therefore, it becomes important to address the completion of these partial point clouds. Recently, supervised methods for point cloud completion have relied on paired complete and partial artificial point clouds for training. However, these approaches face challenges when applied in practical settings due to the significant gap between real-sense data and artificial data. As depicted in the figure, artificial data shows greater uniformity and fewer noises compared to real-sense data. Furthermore, obtaining ground truths for partial real-sense point clouds proved to be difficult, making these supervised methods unable to train effectively. Therefore, an unsupervised approach is necessary to address the completion task under these circumstances. Our goal is to achieve unsupervised completion of real-sense partial point clouds, specifically focusing on objects such as chairs and tables, shown on the left side of the figure. On the right side, we present the completion results obtained using our proposed method. Recent unsupervised methods have adopted GANs as the foundation of their frameworks. These methods utilize artificial 3D models as unpaired references to present the target complete shape. The core concept revolves around transforming latent codes from the space of partial real-sense data to the space of complete artificial data, followed by decoding to generate a complete point cloud. However, these approaches often face challenges in preserving the shape. As depicted in the figure, the result of the unpaired shows noticeable shortcomings, such as the absence of certain details like the chair arm. Notably, similar limitations can be observed even in supervised methods. Additionally, recent work in the field has struggled to achieve uniform and accurate results. We introduce an supervised symmetric shape-preserving autoencoding network, which is designed as a GAN-based end-to-end network that does not rely on pre-trained weights. We leverage the inherent symmetries observed in various nature and man-made objects. As depicted in the figure, we introduce a novel symmetry learning model that generates symmetric point clouds of existing object paths by predicting the corresponding symmetric planes. In case where direct inference from the input data is not possible, we utilize an initial cost module to provide an initial prediction. Commencing from the initial guess, we have developed a refinement autoencoder with an upsampling refinement module which focuses on detail refinement and a local feature grouping module for extracting local information. This design aims to facilitate the learning of intricate structures within artificial data through the autoencoding process. In addition to the indirect guidance provided by the feature discriminator in the latent space, our approach incorporates a point discriminator that directly utilizes the predicted point clouds as guidance to generate more accurate shapes. Furthermore, when dealing with multi-category data, the discriminator can be replaced with a classifier. This allows our method to simultaneously classify the input data with consistent performance. In recent unsupervised approaches like Compare, the accuracy of a point cloud classifier is utilized as the evaluation method for assessing the completion results. The underlying assumption is that the better the completion results, the more accurate the classifier will be. However, we take a different approach by constructing a dataset using annotations from scan to CAD derived from ScanNet and ShapeNet. This dataset comprises real-sense partial point clouds along with paired complete ground truths, enabling a more accurate evaluation of the completion results. Here is a comparison of our method against previous approaches. demonstrating that our method achieves sorter performance in unsupervised compilation of real-sense objects. In contrast to previous methods that train each category separately, our method offers the advantage of simultaneously classification of partial point clouds when applied to multi-category data. This is achieved through the utilization of a classifier-guided discriminator, while still maintaining performance when trained on single-category data. The red figure demonstrates that our method shows a more organized distribution in the latent space as compared to previous approaches. Below are the compilation results of real-sense point clouds showing the superior performance of our method in handling real-world data. Our approach demonstrates enhanced robustness, generating more accurate and uniform results while preserving existing details. In conclusion, our proposed unsupervised network for real-sense point cloud compilation offers several key advantages. It effectively preserves the symmetric shape of objects and exhibits applicability to multi-category data. Furthermore, the compilation results generated by our method are more accurate and uniform. Additionally, we introduce a novel evaluation method specifically designed for real-sense point cloud compilation. Thank you for attending my presentation. If you are interested in our work, you can scan the provided QR code for more information.